the afternoon session. Okay, so welcome back, everyone, to this second part. Okay, so today I will just finish up some small things from last time, because last time we ended up writing the script that simulates this transverse easing model, but we didn't quite finish. And then after that, I want to go to a way of doing it in a better way using sparse matrices. So just to remind you again, so essentially what we did the last time, first we had discussed kind of how to really write down numbers, just complex number in your computer memory. And then the second part was just how one does exact diagonalization, so full diagonalization of your problem that helps you then to solve all of the time evolution. And then we applied this for the spin model dynamics, where we have this transverse easing model with one flipped spin in the beginning, and then just looking at the evolution of this. And we stopped kind of around, oops, was it? We stopped around here, essentially. So, of course, we didn't plot anything yet so far. We just evolved our vector. And the last step I wanted to do is just to show how to plot now the time evolution, so of the sigma set expectation value, which is very easy to do because it really just is this, just literally just computing this inner product here. So with this, I will just do this very quickly. So just to remind you everything. So this is the script that we had written the last time. I hope the font size is still big enough. Yeah, so to remind you, we had this, we wrote a function to build these spin operators. So that was really just the function to, from the small 2x2 matrices, go to the full matrices on the big Hilbert space using these Kronecker products. And with this, we created sigma x and sigma z operators. And then from this, we had a function to build the Hamiltonian using this set of matrices. And then we started writing a function that does the actual time evolution here, which the most expensive and key part is really this one here, where we build the Hamiltonian. We take some initial state. This is the state where we flip the spin in the center of this chain. So we start with the all-down state, then we flip the state, and then we just did here this matrix exponential for an infinitesimal, not infinitesimal, but for a very small time step, that when every time I apply this operator, I evolve my state. Right, so the expensive part of this whole calculation is really here, building this matrix exponential, because this is where the diagonalization happens, and this is the expensive part, and then the rest of it is just applying a matrix to a vector all the time, which is quite efficient. Okay, but so far, everything we just did is just really checking at each time. We just checked how good is the norm of the state, because this was just a sanity check, because in case that the norm goes crazy, then we know something is definitely wrong. Okay, and so far this worked. So in the sense that I now, if I call this function, I call it for like 10 spins. Here, these are the parameters that I enter. This was the hopping strength, to remind you, from this transverse easing model, so the sigma z type interaction. This alpha was the decay exponent of this interaction. Let's set it to 3, and then this transverse field strength was x. And then we can simulate this over small time steps, let's say 100 of them. And then this is, oops, yeah. So this is what did the evolution. And I see I have now 100 steps every time I update my state, and the norm stays okay. Okay, good. So the question is now just how to really output this sigma z variable. So I want to make now a plot exactly as I had it over here. So this color-coded heat map, if you like, where on this horizontal axis I have the number of the qubit, the spin that I look at. The time goes along this axis up, and the color-coded thing would be the value now of this expectation value of sigma z. Okay, let's just do this. I mean, this is now really warming up. So what I want to do is, of course, now here I'm in my loop over the the time. Actually, I like to evaluate these observables before I do the actual evolution. So now if I evaluate things here, then it would be in the first time step, the expectation value at time 0, and then I get the ones at later times. So here what I want to do is really I want to do something like psi dagger. Right, this is the bra of the psi, this is the Hermitian conjugate of my state vector, times now the sigma z operator, which I have defined for all of the spins. So let's say this is of I, and then times psi. And I want to get this for all of my spins. So I can loop for all of the spins, 1 to n. And that's it. Right, so now the question is just to output this variable. What I have to do is I have to now define something before. Right, so my output will be really for each point in space and for each point in time, I want to have this value. So I will want to write this into a matrix. Let's define a matrix which has steps times of, this is the dimension of the numbers of time steps that I have. I just put it in this direction, and the number of spins in the other direction. Right? So because here at each point of time, I now can fill this matrix without a set. So this is for the time. This is the first dimension, which is the column in the index of the rows. Sorry, so confusing. And the second index is just II, and this is how I save this matrix here. And then all what I want to do is, at the end of this function, I want to return this. Okay, so now this should work because at every time step, so for every point in time and for every point in space, I compute the value of this expectation value as set. Okay? Great, let me see where I introduced the bug. No, it even works, amazing. And now let's see what comes out of this. So this should now, is now a function. This should do the time evolution and then should output this full matrix. So let's see if it gives something reasonable. I forgot to include, that's why it worked. So I include the script again because I updated the function. And now this should work. Exactly, and this is the output of the function. I get a 100 times 10 matrix, 100 because I have 100 steps, and 10 because I have 10 of those spins. So now it's going to be the time to make a plot of this, and I said I wanted to do a heat map, so I'd use something called heat map, and I plot this function. Okay, now I have to just be a bit careful what I put on the horizontal axis and the vertical axis. And here I go 1 to 11. This was for my, for 10 I did it, I think. Yeah, this was for 10 spins. Well, let's just do it like this first. And let's see what happens here. There it is. Right, so this is the evolution of the Z thing and the Y thing. Okay, so all I want to do now, I want to cheat a little bit and just to make this plot a bit nicer, I just copy some things like this to make this plot. Oh no, so sorry, I wanted to do one last thing first. With this I actually wanted to now go back to really the final thing of saying, okay, now putting everything really together into one thing and to really write the script that does everything what you want to do. So this is a question I got earlier. So the way that I code things here, it's kind of a functional programming style, which means that I really define functions that do several tasks. But then in the end, when I really write a program, what I do here is I had this function at the beginning that I defined, which was the main function. I just call it main. You can call it whatever you want. But main is just because in C, one use this main function. And so far, this didn't do anything, but this is what I really want to be my program. Right, so here I have this full script that I really include. It just defines all of this function. And then I have this main function that does actually really all of the things that I want to do. In this case, is I want to run the time evolution, and then I want to do the plots in the system. Right, so in the main function now I would put really everything together. So this one I had this sigma minus operator before I had defined globally. Now I define it here, hopefully without any bugs. Then I was making my spin operators. Right, this was this spin operators from this sigma minus operator and from the number of spins that I use. Oh, sorry, do I have the wrong thing? Oh, sorry, I'm stupid. This is what I define in the other function. So I want to actually start with sort of the number, just defining the parameters that I use. So I start with the number of spins, right? So I define my hopping was 1. I want to do something like my decay exponent of the Ising model. I'm going to choose it something like 1.36 because this is what they had in this experiment specifically. And then I have a transverse field, which I just use 1. I need a time step. Again, this time step is not really, I don't need a time step for an approximation. This is really the steps at which I want to evaluate my expectation value. And I had the numbers of steps, which was in this case, we choose 100. Okay, and then what I actually did is I had this full function that does the evolution and gives me back this sigma set expectation values, which was this function that I called TI simulation, where I just give it the parameters n, j, alpha, hx, dt steps. Okay, and now is the point I wanted to cheat. I want to make the plot. Okay, so instead of printing hello world, I make now a hello world, I make a nice plot. This is just, all of this is just plotting to make the column maps a bit nicer, to make the ticks properly and everything, to make proper labels using LaTeX notation and so on. And then I just display this plot, and let me see now if this works. So now the idea is that I really include all of these functions that I had. And after I include everything, I can do this main function, which should now make my plot that I want. Here it is. Okay? And if you have this plot, and if you want to write it to a file, one can just save this figure here in the script as a file, and then you can put it in your paper and publish something. That's the general idea. Okay, great. So the one thing that still, of course, now let me go back to the slides. Okay, so this is what we really produce now. So I hope I showed you that it's quite easy to produce something like this. So now, of course, you can ask, does it match? And then if you look in this paper here, it's actually quite confusingly written, and I didn't even find actually the transverse field strength, so that's a bit worrisome. So, but I encourage you to kind of play a little bit with the parameters to see, to maybe find the transverse field that then matches the evolution like this. But it is actually quite similar, which is maybe not so easy to see here because the contrast is not very good. But essentially, one has characteristics, one has these two revivals happening on the edge, for example, and this is also happening here in this case for this plot. So I just encourage you to play a little bit with this, but I don't really want to go too much into the physics of this right now. Okay, good. So finally, really, what I wanted to say is what really should bother you a bit is that we have these gigantic matrices, right? You have all of these values which are mostly 0. And this is just because the Hamiltonian is really lives on a gigantic Hilbert space, right? It's a 2 to the power n times 2 to the power n matrix. But then if I look at the coupling matrix of my spins, it's just an n by n matrix, right? So I have only 2 body terms, so I always have sigma z times sigma z, and I have only n squared of those terms. So even if I have long-range interactions, even if I have all of these terms coupled to each other, the matrix is still going to be extremely sparse, right? Because I still completely neglect terms where I could have sigma z, sigma z, sigma z, sigma z, sigma z acting on like several spins at the same time. And those would be terms to actually fill up these kind of other elements of this matrix. Good, but at the moment, we don't have them. For example, if I take this Hamiltonian that I built before, and if I just ask how many elements are larger than 0, right? As I said, larger than 0 should mean something larger than machine precision. So I can check, for example, the sum of all of the elements of the Hamiltonian larger than 10 to the minus 16. And then I should compare this to the number of elements in the matrix. So in this example, I had, again, 10 spins. So 1024 times 1024 matrix, 2 to the 20. And this number here is only about 1%. So only 1% of the values in this matrix are actually non-zero, and 99% are zero. Right, so you're wasting a lot of energy, yeah, that too, a lot of memory if you store all these zeros, because it's just gigantic bit strings of zero that lie in your memory and they are unused. So instead, one should really use what's called a sparse matrix. A sparse matrix is really just a different way of storing the data. So you don't store the matrix in a linear form, but you just store the non-zero elements and where they are. Right, so you say you need 2 integers, for example, 5 and 6, then the element 5, 6 of that matrix would be followed by a number and a floating point. Right, so now for each non-zero number, you need 2 integers and 1 floating point, but still this totally pays off in this case because I only need 1% of the floating point numbers that I would use usually for the full matrix. Okay, and that's the idea. So just in Julia, I will do this just in the next part. It's actually now, in the code that we had, it's completely trivial to switch to a sparse matrix thing, right? Because I started with my definition of this sigma minus operator, and everything of the sigma minus was based on the sigma minus operator, right? So really all I have to do from the very beginning, I just have to define this little thing as a sparse matrix, which if I do that, you will see that something like this comes out, right? So now you see you have this 2 by 2 matrix here. So these elements are non-existent because they are 0. And the only thing that you store is this little 1 here. Okay, and now, because this is already defined as a sparse matrix, if I use this Kronecker product function, it just will keep the sparsity of the whole problem, right? The Kronecker function knows how to do a tensor product between 2 sparse matrices, giving you a new big sparse matrix. Right, so really nothing in this code needs to change. Well, almost nothing. The only thing that we will need to change is that here we had these identity matrices. Remember, these were the identity matrices for the left part of my Hilbert space. Then there was the spin operator, and then I had the identity for the right part of the Hilbert space. So all of those I only have to define now as a sparse matrix. So instead of defining them before like matrix of the identity operation, I define it now as sparse of the identity operation. This would be a sparse identity matrix in this case. And the only other thing is then in the Hamiltonian function, we just have to start with a Hamiltonian, which is not all zeros, but which is a sparse matrix, which all zeros, which in Julia you can use this function here. And that's these 3 little changes that you have to make your code. And then you can construct easily the Hamiltonian now as a fully sparse matrix. And it really pays off. For example, this was, if I do this, if I just measure again the time of defining a sigma minus operator and building the spin operators and then building the Hamiltonian from these spin operators. Here on some machine, on this laptop, I think it was 0.8 seconds. But now if I do this with the sparse version, I find that this is almost 2 orders of magnitude slower. Right? So already here things get much faster. This is nice. But still we are suffering from one fundamental issue. And that is still our full diagonalization does not really work with sparse matrices. Right? And the reason for that is just, I told you, like full exact diagonalization. What it does, it just computes this matrix V. So the V is the matrix where each column of this matrix is an eigenstate of the system. But now if I do this, I create, like again, Hilbert space 2 to the n eigenstates. So this matrix V is going to be, again, a full matrix. Right? So this is really going to have 2 to the 20 elements. This is by default not sparse. So at the moment, we cannot really use that. Right? So if I do full diagonalization, I may as well just start with a full matrix because I need the memory anyway. Okay. Now this is, oh, wait, I have one more comment here. Sorry, I wanted to really do this also. One last comment, okay, now just a bit physics just to show you that what I showed you and the construction is really actually quite general. So here we talk about light atom couplings, right? So you may also want to, for example, simulate a photon mode. Or what you may want to do, this is you will learn in the next week, I think. There's an optical lattice lecture. They have things like the so-called Bose-Hubbard model where you have bosonic particles that can be on lattice sites and they can hop around, that they can interact. And just I want to say everything what I said here, the construction of Hamiltonians works equally well for bosons. One just has to do one different thing if I want to have a bosonic particle or an harmonic oscillator in my problem. Right, so far we had the spin lowering operator, but equally one can also very simply just define a sparse bosonic operator or a sparse ladder operator. Well, so the way that this works, I can define now my Hilbert space with, for example, the Fock state 0 of a harmonic oscillator being 1, 0, 0, 0, and so on. And I have to cut off this space at one point. Let's say I go up to occupations of like 10 photons or something. And then I have this type of Fock states being really just, again, these basis states. So then I do this cutoff, and then I can define sort of a sparse ladder operator in this way. Right? So this is really what this is doing. It's really creating something like, right, so before we had our spin lowering operator was really the matrix where I had 0, 1, 0, 0 here. Right, and the spin lowering and the bosonic ladder operator is just I have a square root of 2 here, 0, 0, and then have a square root of 3 here, and so on. Right, so this would be the typical ladder operator for your harmonic oscillator. And I can also, I give you here the sparse version of creating this operator. So then you can also use a Kronecker product and do terms, for example, like a spin together with coupling to a photon. You would write it exactly in the same way. Right, so it's a really nice general thing to really just start from the fundamental lowering operators and then construct everything from there. It really does not need any much changes in your code. So this is just a comment I wanted to do. I don't want to talk a lot about bosonic models here. I will come to that back a little bit later. Okay, good. So with this, I want to start the second lecture now. All right, so the second part was the recap. I already did this, and this was the problem that we had. Just simply, so how do we deal with this now? Okay, so today I will do two parts of the lecture mostly. The first one will be now really doing the spin model simulations using these sparse Hamiltonians, only with the difference that now we're just going to introduce the so-called Krylov space, which is a very nice concept. And I think it's the best way of really simulating dynamics with Hamiltonians that only have few body terms. So that's the first part, and then the second part I really want to do again, go back to the code and really simulate the spin model that we did before, now with sparse matrices, and now showing you that one can do essentially just much larger systems than before. And then after that, I had foreseen that I talk a little bit about simulating open system dynamics. I honestly don't think I have really time to go through that. So in case that I don't make it, I will just leave that there, and I will just leave it in the notes that will be uploaded eventually. Okay, good. So the problem. So this is what I mentioned before. So just to remind you, what our goal really is we want to simulate time evolution of the Schrödinger equation with a time-independent Hamiltonian, where the solution to the problem is simply given by the matrix exponential of this applied to some initial state. And generally, the Hamiltonian is going to be very, very sparse. Okay, so this is a problem that is, one could use a general ODE solver that we go back later, but this would be really overkill because the problem is a linear problem, plus the Hamiltonian is time independent. Okay, so it would be great to do again this direct computation of this matrix exponential with the sparse matrix, but as I mentioned before, here, if I look at my spectral decomposition of the Hamiltonian, then I would have capital D eigenvectors here, which are all full eigenvectors, and my full matrix would be full. Yeah, so I cannot really make use of the sparse matrix. So the obvious idea is to go back to the definition of this matrix exponential applied to some initial state, which was defined as really this full Taylor series of the exponential function. So here minus IT Hamiltonian with some power divided by k factorial applied to some initial state. So the obvious idea is that if I look at this sum here that defines this Taylor expansion, I write it here as a power of some matrix that I call A. the obvious idea is that maybe, to do that evolution from some initial state, right, maybe we don't have to sum over all of the eigenstates of the Hilbert space, but maybe we only need a few terms in this sum. Right, this is kind of intuitive, because if I evolve my state from some initial state to some final state, now of course if I evolve it over a very long time, this state may visit all of the Hilbert space, but actually it's quite likely that if I simulate only a little time step that I want to do anyway, then I maybe only need a few eigenstates in the system to evolve me to the next state. The question is just how to find those eigenstates efficiently. And this is what this Krylov space is about, essentially. So the idea is that I define a space which is much smaller than the Hilbert space, which is called the Krylov space, and inspired by this sum here, where I apply powers of this matrix to my initial state. The idea is that I use the basis states of this sum. So I define basis states where I apply this Hamiltonian not at all. I just take the initial state. This is a to the power 0. This is an identity. Then I define a state where I apply this a 1 time, I apply it 2 times, and so on, and I apply it k times. And this is the basis that I want to keep using. Okay, and this was essentially invented by this Russian engineer. It's just always like when I'm giving lecture, it gives you time to look at some historical facts, looking up some people. And then like people nowadays, they always complain that they have to publish so many papers, but then look at this guy here, over 300 papers and books in all over the field, so I don't know, pretty impressive. Okay, so anyway, so that's the idea. We want to use a space that is defined by these vectors to rewrite our problems, just given by the intuition that this should be really a good space for our problem, because all of these states, they show up in this sum here. There's only one fundamental problem with this, and this is, if I look at these states, they are not orthogonal to each other. Right, this is actually quite easy to see if one goes to a very extreme limit. So let's, for example, for a second, just say that the A is the Hamiltonian. So here it's actually imaginary unit time times Hamiltonian, but let's just say it's the Hamiltonian for a second. And now if I decompose my initial state that I look at into the eigenstates of this Hamiltonian, so this can be a random state with some coefficients, and let's say that I order the eigen energies that I have, so E1 is larger, E2, E3, and so on. Now, if I look at my Krylov state, which would be this Hamiltonian k time applied to the initial state, then this is obviously just a state where I apply the eigenvalue to the power of k to my eigenvectors. And now if I make k very, very large, and if I renormalize my state, then I see, of course, that C1 times E1 to the power of k is going to be much, much larger than C2 times E2 to the power of k. Right? So if I make k very, very large, I rotate my state closer and closer to the largest eigenenergy in the system. Right, so this is, let's see if I wanted to check this. Yeah, let me go to the back. This is something that we can, for example, just very quickly, because it's actually really funny that this works. Right, so here I can use the, let's build just a Hamiltonian for a second. Right, this was again 1, 3, I build a random Hamiltonian, random field. Okay, I have not defined my spin operators. Let's take for 10. Right, so this is just so that I have some Hamiltonian around. Right, and then let's, for example, right, if I look at just the eigenvalues of this Hamiltonian, right, so nice thing about Julia, it already sorts the eigenvalues directly. So the columns in your V matrix, they're already sorted. So the largest eigenvalue would be the one with this eigenenergy here. So I could get this eigenvector if I say, where is a very simple function. Right, so this is now something that gives me really only the V matrix, and I know that the last column that I have here is going to be the largest eigenvector in the system. So I take the last column, I can do it like this, And this is the largest eigenvector in the system. Okay, so now let's just say instead, I now just make a completely random state. I call it vec underscore it because I want to iterate that state. And let's just make it a random state of 1024 elements. And let's make it a normalized state because it should be kind of a quantum state. Norm of this. Right, so this just, what these two commands do, they create, if I would not make a mistake, all the time. What did I do? I did accidentally a double point instead of a semicolon. Right, so this makes the state and this normalizes it. So now the norm of this state is 1. And it's just a completely random state with random numbers filled in. Right, so if I want to compute the overlap of this state with the eigenvector, the largest eigenvector in the system that I have, I do just this. Right, I should actually take abs of this squared, right? So this is really the norm squared, which should make it a probability. And I see it's like it's not 1, right? So this state is in the Hilbert space pointing in some direction, so it's not the initial state. Right, so what I have now is I have really my Hilbert space. If I sketch this, I sketch it, of course, just as a 2-dimensional space. And at the moment, I have now the largest eigenvector in the system, E1. So this is the one that I called EV here in the code. And now I have some other state which is completely random that points in some other direction. Right, and now what I can do is I can just take this state and I iterate things, and I just take the state, apply the Hamiltonian one time to it. And then afterwards, I check again what is the overlap of the new state, after I normalize it, of course. So what I do here is first I apply the Hamiltonian. Just I overwrite the state with the state after I apply the Hamiltonian. Then I normalize the state, and then I check what the overlap is again with my Hamiltonian largest eigenstate. And you see, now it's 0.4, now it's 0.5, and I keep doing this as many times as I want, and I go towards 1. Right, which is actually a pretty cool, pretty ridiculous method to find the largest eigenstate of a matrix. It's also called the power method. Not because it's powerful, but because you take the power of the matrix. And you just keep applying the same matrix over and over to some random state, and you slowly converge against the largest eigenstate of the system. Right, so here now I have then the state where I have Hamiltonian, well, this is a matrix now, times my vector and so on. And then I do it to the power 3, 2 to the power 3, and I rotate closer and closer to my largest eigenstate in the system. Okay, and that's called the power method, of course, with one little loophole. The loophole is that, of course, your random initial state must have some overlap with this state. If you start with an orthogonal state, then you may never find this. Okay, good. So this was just really to show this concept of these Krylov vectors, and the problem that we have that they become more and more aligned the larger I choose this power. Good. So we have to fix this. And I'm sure many of you heard how to fix this. So how do you make vectors orthogonal? It's written here. You use what's called the Gram-Schmidt procedure. Right, so the idea of creating a good basis for our problem, it's called, for the general matrices here, it's called the Arnoldi iteration, named after this person here, which is one of these very few persons where there actually is absolutely no picture on the internet. I don't know how this is possible, but it's really true. Okay, and so the Gram-Schmidt is just starting from some set of non-orthogonal vectors. You make them orthogonal, right? So here I show you how this is done now for our problem. So I use here really the bracket notation always for this. But of course, the scheme is completely general. This works with any vector space, with any matrices. Okay, good. So what's the idea of making the states orthogonal, this Gram-Schmidt procedure? Well, I start with my initial state that I already know, and I assume that it's normalized. So this is the first vector of my Krylov space. And now I want to just find the next Krylov vector where I apply it one time, this matrix, and I want this new vector to be orthogonal to my previous vector. So how do I do this? So this is all written in this first little box here. So I define my state psi1 first as the unnormalized vector where I apply this matrix to my state psi0. And now what I have to do is I have to subtract the component of the previous state, of the psi0 state, proportional with the overlap that this state has in psi1. Right, so the idea is I compute the overlap between psi0 and psi1. This is just a number, right, an inner product between psi0 and psi1. This number I call h1, 1. You will see later why I just use this notation. But for now, it's just a choice. And then I define my new state psi1 as the state psi1 minus the h11 times the psi0. Okay, and now I really subtracted the psi0 component in the state psi1. So all I need to do is I have to renormalize my state. So I have to compute the norm of the state psi1, which I call h21. And then I divide by this. Okay, so now I have two vectors. I have the vector psi0, I have the vector psi1, and I know that they are orthonormal to each other because they are orthogonal because I subtracted this overlapping part with psi0, and I normalized it after that. Okay, so that's kind of the first iteration step. Now, in general, of course, you now keep going with this scheme. So in the iteration number I, for example, what you do is, so for example, the second one, you apply the matrix again to the previous state. And now, in order to make this new state orthogonal with all of the other previous states that I have to loop through all of the previous states and really subtract all of the weights that they have in this new state. Right, so I start computing the overlap with the state psi0 of this new state, of the state psi and I subtract it. Then I compute the overlap with the state psi1 and so on, all the way up to the overlap psi minus 1, psi, and I subtract it. And all of these overlaps I keep track of, and I call them H, and I really write them in a matrix, as you see. So I have here now matrix element of this little matrix H, which you will see later what this matrix will be. So one I element, this is the overlap of the state 1, 2I, the other overlap element, and so on. And then when I'm finished with this, I just compute the norm again of my state and I renormalize it accordingly. There's one little detail hidden here. So what I show you here is the so-called modified Gram-Schmidt procedure. There's also an original Gram-Schmidt procedure, which is numerically not so stable. Modified just means that if I go in this loop here, if I go to subtract the second state from my state psi I already use the updated state here, right? So here I already update my state psi by subtracting this component of psi0, and then I use this new state to again compute the overlap of the other state. Right, in the original Gram-Schmidt only, you just take all of the overlaps with all of the states, and then you subtract them. Right, but here I iteratively do it, and this is called modified Gram-Schmidt, and this is numerically more stable than the original one. But it is just a technical detail. Okay, so far so clear. So this is really linear algebra basics. Okay, good. So what do we do effectively if we keep going with this iteration? So how do we gain any progress here? So on the one hand, what we do is, you see, we create all of the set of these Krylov vectors, which are now a new, nice, orthonormal basis set for our problem. So what I can do is, I can, for my iteration I can write all of the vectors that I have already in this matrix. Right, so this is a matrix, I just write it like this, but each of these ket vectors, I think about it as a column vector. Right, so this matrix Qi is actually a D times I plus 1 matrix. at iteration I. So this is let's say I keep going and then I stop at iteration I, and then this is the matrix that I have. But because I constructed them in an orthonormal way, I know that this Q in this case is really a semi-unitary matrix, meaning that Q dagger Q is again the identity. Right? So if I do Q dagger, I just build the Hermitian conjugate of this thing here. And then, of course, all of the different Krylov states are going to be orthogonal. The same one is just going to be normal, so this is going to give me an identity. Okay, so the question is now just what is this matrix H that we defined here? Right? So this was all of these overlaps in our procedure when we constructed this Krylov basis. We kept track of these numbers, these overlaps, and we wrote them in a matrix. This matrix is now a I plus 1 times I matrix in iteration I, and it has this so-called upper Hessenberg form, meaning that it's only filled really on the upper diagonal and one row on the lower diagonal. Okay, doesn't really matter. Good. So what is this matrix? So in order to understand what this matrix is, I want to just quickly convince you that this iteration that I did here, this iteration, I can also write it in a matrix form. And if I write this iteration in a matrix form, I can write it like matrix A applied to this matrix Q is at iteration I is the same as the matrix at iteration I plus 1 times this H matrix. So I'm not going to really show the full proof of this, but I just give you the example for the first iteration. In the very first iteration, my first orthogonal vector I constructed with by first doing A applied to psi 0. Then I was subtracting this element H11. And then I was dividing by the element H21. So if you look at this expression, I can just massage it a bit. I bring this on the other side. Then I just bring this on the side over there. So I can write this equation just as A applied to the state psi 0 is H11 times psi 0 plus H21 times 1 times psi 1. Right? And this equation I can write again in a matrix form. If I think about this thing here as a 1-by-1 matrix, right, it is a bit of a silly way of writing it. But at the first iteration, Qi is really just a 1-by-1 matrix. Well, it has one vector psi 0. And here I can write it like this, where this is a 1 times 2, and this is a 2 times 1 matrix. So this gives me psi 0 times H11 plus psi 1 times H21. Right, and now this, if you look at this, if you stare long enough, then this is exactly this expression here, because my Q is defined as having the columns as these vectors. Right, so this is Qi, this is Qi plus 1, this is A, and this is the Hi at the first iteration. And now if you want to prove that this is true for future iterations too, one just has to do induction showing that if it's true for I, it's also true for I plus 1, and then you can do this if you want. Okay, good. So, but what does then mean if we? So, of course, at one point we want to stop with this iteration, and let's see what it means if we stop this iteration. So, at one point I arrive at my matrix Qi plus 1, but then I'm not interested to go any further. So, what I want to do is I want to throw away this last Krylov vector. I don't need it anymore. And equivalently, in this matrix Hi, I just want to throw away this last row that I have. Okay, so when I really terminate this iteration, it means that I really stop, and I think I'm happy with all of my my problem, which means that I define this new matrix here, H tilde, where I cancel out this thing, and I also say then essentially that my new Qi plus 1H is the same as Qi times H. Okay, and now what's very cool to see is essentially that because of the form of this iteration in matrix form, this matrix now looks like A Qi is the same as Qi Hi, but I know that this was again this unitary matrix. So here I can now multiply this Q from the left side or from the right side to this equation, and then I see essentially that this matrix H tilde here, so just the matrix with these numbers here, is actually already the matrix A projected to the Krylov state. Right, so it's kind of the way that one would usually think about it. I construct this matrix Q, which is the projection matrix to my Krylov space. Then I could take my Hilbert space problem, map it to this Krylov space, solve things there. But if I do this iteration and if I just store these numbers, I already get the projection of this matrix A automatically. I don't have to do anything anymore. Right? So this is nice. So this really means that the matrix H is really an approximation of this bigger matrix A in this much smaller Krylov space. Okay, so here's now the strategy about what we really want to do. I just said it already, kind of. So we want to start. So this is really just a sketch, right? So this is not really mathematically sound. But what we want to do is the following. Our original problem was doing a matrix exponential, right? So we had the big Hilbert space. We have the matrix A, which is going to be a sparse matrix, and we have some state psi 0. And we want to get to an approximation of the matrix exponential of this matrix A applied to the matrix psi 0. But we don't want to do it on this big Hilbert space, but instead we do is we map this problem on the smaller Hilbert space, where my matrix A becomes the matrix small h. Then I have to map my initial state psi 0, becomes some small vector v. Then I solve this small problem here on the small Krylov space, and then afterwards I map it back to get an approximation of my big thing. Right? So that way I really avoid doing this whole problem on the big Hilbert space, but I just can do it on a controllably smaller space. Okay, so just one little remark here at this point. So for time evolution, our matrix A is going to be minus imaginary time multiplied with the Hamiltonian. If I really choose this matrix A to be the Hamiltonian itself, then actually the matrix A that one has is much simpler. It has than just this so-called tri-diagonal form. So then only diagonals and upper and lower diagonals are filled and everything else is 0. And then, for example, if I want to compute the lowest eigenstate of a system, this is very efficient because this is really trivial to diagonalize at a matrix like this. And then in this case, one uses a slightly different iteration, which is called the Lanczos iteration. So the Lanczos iteration is sort of Krylov space construction for a Hamiltonian. And this Arnoldi iteration is for a general matrix. Here, since our matrix is not the Hamiltonian, it's not the Hermitian matrix, it's minus I times the Hermitian matrix. That's why we have to use the Arnoldi iteration. Okay, good. So I will just start playing with this again in a second. So here I just wrote to you everything what I just said in just a few lines of codes. I don't really want to type this on the fly because I'm sure I'm going to make a mistake. It's too many lines to not introduce any bugs. But this is how it looks like, and then afterwards we're gonna play with this. Right, so this is now really a function which does this matrix exponential using this Arnoldi iteration for an arbitrary matrix A and some initial state psi 0 using a maximum of m Krylov vectors in the problem. Right, so now this is of course very different from the full exact diagonalization where we really build the full matrix exponential. And then we just build that matrix, and then we can apply it to an arbitrary state. Here, we really need to have the Hamiltonian, so which we want to build the matrix exponential of, and we need some initial state. Right? So we really don't want to stretch this too far because we don't want to evolve the state over arbitrary long times, but just over little times. So we have to give the initial state, we have to give the matrix, and then we're going to get the state that comes out from the matrix exponential applied to that initial state. Because if I give you back the full matrix exponential, it's going to be a full matrix again, and this is not going to be very useful. Okay, so I have as an argument of this function an arbitrary matrix. I have an arbitrary initial state and this Krylov state vector. Here it's very simple. It's just finding out the Hilbert space size. I could also just pass it on as an argument, but I just can compute it from the length of my state vector. And then what I want to compute here in the beginning, I want to compute this matrix Q, right? So the matrix Q is really this projection matrix where the columns of this matrix will be all of the Krylov vectors. So the Q, I just use this notation here. Similar just means it creates a D times M matrix, because this is going to be dimension D, dimension M. And I use similar, it just means that it takes the same data type as the matrix A. Right? Because I want to have this work for complex matrices and for real matrices, and I don't want to worry about this. So if I use similar, it just uses the same element type as is used in A. And then in addition, I want to construct this version of this matrix A on the Krylov space, which is this small matrix H here, which is then going to be an M by M matrix. It's also be full with zeros, and it's full with zeros, and it's going to have the same element type as A. Okay, and then all of the iteration, which is in this blue box here, right? All of this blue box here is in the blue box there. Right, so I just want to construct this matrix Q. I just say the first column of this matrix is my psi 0. This is the vector that I put in. And then the next following columns, they're going to be the other Krylov vectors. So this loop here just loops from 1 to m minus 1, because I use m Krylov vectors in total. Psi 0 is the first one, so I have to construct m minus 1 more of those. And then for each I, then this is the iteration in here. Right, so first I create the state psi I, again applying this matrix to the initial state psi 0. And then I loop through all of the vectors that I already have, and I do just exactly this iteration. I build this matrix Ji. This is the element here, from the overlap of the previous state, so sorry, of the state J. Here, this is the index J, for example, this one here. Overlap with the state psi I, which is the initial state here. Okay, then I subtract this from my previous vector. This line here is really just the second part of this line here. And finally, I do this normalization, and I normalize it. So I compute the norm, and I normalize it. The norm I write again in this matrix, and this here is just a step when I get my new Krylov vector. Okay. And that's pretty much this whole Arnoldi iteration. And now what I want to return is I want to return the matrix exponential of this matrix A on the Krylov space. So now I use my matrix exponential function, but I use this just on the small matrix H here. Right? If I do that, then I just exponentiate this matrix A. And then I have to map it back on the Hilbert space. And so this, you can see, is a very nice, cute shorthand notation. So what I really want to do is I want to take this initial state, I want to map it on Krylov space, I want to apply the matrix exponential to that state, and then I want to map it back. But this first part here, actually, instead of doing this mapping explicitly, right, I just select the first column of the matrix exponential. Why can I do this? Well, because I just know that psi 0 is sort of the first row in Q dagger. Right, the psi 0 is the first column in Q, so it's going to be the first row in Q dagger. So in the other words, I just need to select the first column of e to the power h, and this is going to be equivalent to this mapping. So what I return is, again, it's a full Hilbert space vector, right? Because Q is, again, this matrix that maps me now from this Krylov space back to the full Hilbert space. Okay, great. So actually, let me do this by hand now. Okay, so if you were falling asleep for all of this, so sparse matrix, matrix exponential, let's just play with it. Okay, good. So let's see, how am I doing? Okay. Okay, so what I want to do is now I want to just redo everything what I did before, just using this Krylov function. So what I did is here, I just made a new file, which is just like the old file. It uses a few more packages. It uses sparse array, and it uses this Krylov kit. I will come back to that in a second. And these functions here, I have the one that builds the spin operators. That one I just copied from before, with the only difference that I now use a sparse matrix construction. So this is build sparse spin operators, and I have this function build sparse Hamiltonian, which does exactly the same as before, just making sure that everything stays sparse. And then what I copied in here is really this Arnoldi iteration. thing. Okay, so let's just for a second really play with this Arnoldi iteration. Let me actually restart Julia. So this is now a different file, which was this transverse easing model simulation just in a sparse manner. Okay, it doesn't do anything, but it defined now this function, which is this Arnoldi exponential. Okay, so I really wanted to play with this just with some random matrices just to get a feeling for it. So let's say again we have a Hilbert space dimension. Let's say it's 1024, which is the typical Hilbert space of 10 of these spins in my system. And now let's again create some random Hamiltonian. I don't even make it sparse for now because it doesn't matter. So I want to do a random Hamiltonian, which is dimension d times d. Okay, so it's just some random complex numbers. And now again, I want to make sure that this is a Hermitian matrix. So I want to add to this Hamiltonian, I want to add it just a Hermitian conjugate. Right, so just to make sure that if I do h dagger minus h, it should be 0. Right, okay, so h is a random Hermitian matrix that I just computed. Good, and what I want to do is I have always this matrix A, which in my case is an imaginary unit, times some time step, let's say it's 0.1, times this random Hamiltonian. Right, this is a full random Hamiltonian, nothing to do with spin models, it's just very, very complicated. Okay, so this would be my matrix A. And let's also define a random initial state, why not? Let's also make it complex. Of dimension d, and this should be a normalized state. 0, I divide the state by its norm. Okay. Good, and now I have a fully random state. Right, so if I want to do full diagonalization with this thing, let's see how long this takes. Full diagonalization would be I do exponential of this matrix and I apply it to this initial state. Right, so this would be with this completely random Hamiltonian and this completely random initial state evolved over time that is 0.1. I want to do exact diagonalization. And okay, first time always takes a bit longer. Okay, something like this, 0.77 seconds here. Okay, so let's see how our Krylov thing does. Let's define another vector, which is, let's call it Krylov. And this would be now the one where I use my Arnoldi exponential with this matrix A. Again, my initial state. And let's say, okay, I use 20 Krylov vectors. Equal sign. Okay, so this would be the vector here, so much faster. Very much faster. Very many times in my career, I just optimized and I got factors of 10 speed up only to find out that the result was actually wrong. It's very easy to optimize dramatically. So let's also be fair and check that they are really the same vector. Right, so I do psi ed times psi Krylov. Right, I do the fidelity of this thing. And I did something wrong. This is not nicely done. And it's 1. Right, so I get the same evolved state just in a much faster time using just these few iteration steps. And the reason is just because I didn't need to diagonalize any big matrix anymore. I only diagonalized the 20 by 20 matrix. And this is the idea of the whole thing. So let's see how well this thing is doing. Right, so let's do this whole thing and let's always check again the overlap always. So let's say psi ed times psi Krylov and squared absolute value. Okay, so this is what I just did before. Okay, so let's play with the number of Krylov vector. Let's see how many states we need. Right, so now I use just 10 and well, it's still pretty good. Right, it's not exactly 1 anymore. You see small deviations. If I use 5, yeah, now things start to go to hell. Right, not only this is not 1, it also becomes unnormalized and catastrophe happens. So 20 was kind of a good choice. But now the important thing to understand in terms of the physics here, let's see if we actually choose a smaller time evolution step. Right, let's not go to Well, let's make it much smaller. Let's not choose 0.1, but let's choose 0.01 only as an evolution time. Right, so now I have a fully new matrix, so I should also do my exact one again. Okay, and now let's see, with my 5 Krylov vectors, now I get almost a perfect result already just using 5 vectors. Okay, and this is the physics I want to get across by this method. This is what I always mean. When you do some of these methods, there's always some physics behind that you can understand. And here it just really means, so this is what I should show you. So here, what I just did is a little plot of exactly the problem that I used now. So I used a completely random Hamiltonian, a time evolution. And what I compute is I compute the fidelity of this problem. So the fidelity of the exact solution with the Krylov space solution. And I plot 1 minus the fidelity. So this is a number. If I get an exact result, this should be 0. Right, and you see now if I choose a small time step, then here, this is the number of Krylov vectors that I need. This is this infidelity. I see this is bad, 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 but then it drops very quickly to 0, which again is something like 10 to the minus 15. Again, all is relative numerically. But I see I need about 15 Krylov vectors to get the fully exact state vector for this evolution. However, if I make the time step larger and larger, I need more and more Krylov vectors. Right? And this is really telling you the physics about you start from some initial state, then you project it onto some eigenstates, you add some phases, and then you get a new state. But you don't need all of the eigenstates of the Hilbert space in order to do the evolution. But the longer you evolve, the more of those states you will need, especially for this fully random Hamiltonian that I have created here. Right? So this is really the physics behind matrix exponential on a small space is enough for a small time evolution step. But the longer I evolve, the more of the Hilbert space I'm going to explore, the more of these Krylov vectors I'm going to need. Right? So you always will have this trade-off between making your Krylov space larger or making your time evolution shorter. But typically something like 0.1 is anyway nice because we saw before to get nice plots, this is a nice time step that one should choose. So I recommend just picking that and then adapting these Krylov vectors accordingly. All right, half an hour left. Okay, good. So then finally just a comment here. So right now that we understood how this works, I wrote our own little script. Now, of course, I mean, this is still a very rudimentary script because I want to have, for example, a way of really determining how big my error is in the function, or I want to have some way of doing this Arnoldi iteration and stopping automatically once the error is small enough. And this, of course, makes this thing much more complicated. So this writing it explicitly like this was really kind of for educational purpose. Once you know how this works, one can very much fall back to some of the packages. In Julia, for example, there's a so-called Krylov kit, which I would recommend to be using for this type of thing. In other languages, this is called so-called expo kit, exactly the same thing. And there you have now functions like this. So you have this exponentiate function, which takes this matrix A that you want. This thing here is really just the prefactor in front of the matrix. I will use this function in a second, don't worry. And I give it the initial state. And then I can tell it that I want to have the Krylov dimension maximum to some number, right? And I can give it some tolerance also, right? And what this function will, for example, do, if we'll just start with this iteration and just iterate. So if it finds out that it only needs like 5 Krylov vectors in order to get to this tolerant, it will just stop this iteration and not continue any further. It's going to save you another bit of computational time in this case. All right. Good, so now we have everything to go back to more like hands-off, hands-on part. This was the hands-off part. And now I want to do these spin model simulations that we did already before, but now I want to do it using these sparse matrices and just doing it better, really. Okay, so here's the problem I want to look at for today. I want to make it just a slightly bit more complicated. I want to still use really precisely the same Hamiltonian. So I use our transverse field Ising model with the long-range terms. What I want to do a bit more different to show a few more things, I want to start from a different initial state. Because another popular initial state in the so-called spin model quench experiments has been, for example, this nail state, which is a very highly excited state where you just say on every second side you flip the spin initially, so you start with something like spin down, spin up, spin down, spin up. And the other thing I want to also do is to make it more exciting, I want to look at some correlation functions in the system. Right, so far we only looked really at the sigma z expectation value, and then I will also look at some correlation functions. You will see why this is actually quite important to larger systems. All right, good. So this is just on the notes part. So let me get back to this. So I showed you here already, this is exactly the same functions that we are already used to, just written in a sparse form, right? So I can just use them in our usual way. Let's just say, okay, I needed the spin operators, build sparse spin operators, and what was that I needed? I needed to define my sparse sigma minus matrix. 0, 1, 0, 0. What is this sparse sigma minus? Is the first argument of this function, and the second argument was the n. So let's say 10 again. Good. Lots of sparse matrices here. Right. So you have something like, this is quite nice. If you look, for example, now this SX matrix for the first spin, right? You see it looks something like this. So this is the notation that you get if you use sparse matrices. You don't see the numbers of the matrix anymore, but you just see where in the matrix the numbers are non-zero. And this is sigma x. This is why it's this off-diagonal terms only. If I do sigma z, I should get only diagonal terms, yes. Which up to the pixel thing you can do in a terminal, this is diagonal. And the Hamiltonian too, I think. No, this is the old one. This was the random one. So let's now build our sparse Hamiltonian. Again, just now with some j, alpha, 3 random numbers, x, s, s, s. And this is the full sparse Hamiltonian that we have. Okay, good. Now we have the sparse Hamiltonian here. We have our way of doing this Arnoldi exponential. Actually, I'm not going to use this one, but I'm going to use this Krylov kit. Or we can compare them actually. Why not? Okay, good. So now what I want to do is I want to redo. I'm generally very lazy, so I want to redo this function here, which did the simulation of our transverse Ising model. So what I'm going to do is I'm just going to copy this function. General lazy way of doing it. And I'm going to just fix it. Right, so you want to start with this sparse sigma minus spin operators and Hamiltonian, and build, this was just sparse, right? Yeah, this was the function sparse spin operators. And this was the build sparse Hamiltonian. Okay, good. And now let's just shift this one down here. So let's go first until here. So for maybe debugging, what I can do is I can just stop this function here and return like the state vector, right? So right now this function doesn't do anything. I had to include things, of course. I always forget this. Right, so I have to include the whole file again so it sees my new functions that I have defined. And now my relation here. Right, so this was for 10, J, 3, 1, 0.1, 0.1. Right, so far this function doesn't do anything. It just returns the state, which is the initial state here, which is just the state that was the all down state. Okay, but what we want to do is, as I said before, we want to start with now this nail state as an initial state. Right, so let me actually go to this one here. Was it? Okay, so how would we do that? Right, if you want to start with this nail state, any ideas how to do it? Well, I mean, we can just do what we did before. Like before, we started with just one spin flipped. So now we can just flip every second spin using the SX operator, right? So we could just do a 4 I equals 1, and now I do a nice trick. I do 1 in steps of 2 to n. Right, so now this is a loop where this index II is not 1, 2, 3, 4, 5. It just goes 1, 3, 5. It takes all the odd numbers. And then why not just define the state here? Psi is Sx of I applied to psi. And right, and now I will get the nail state initially. Okay, let's just write out. I just always have to include, so let me write it like this. It's going to be easier. Then I don't have to do all of this stuff all the time. Okay, now I get this. Let me get it here to the terminal so I use it. Right, so now I have this state psi, which is the nail state. And it looks funny, right, because it is all zeros almost everywhere. But it actually does not, right, because if I, if I look where, for example, now the modulus of this, right, so if I take the element-wise modulus and I ask where is this element-wise larger than 0, right, and then I can do a find all. Right, I see there's one element that is in this vector which is actually non-zero, of course, right? Because this is, now if I take this number here, let's see what it is. Wait, I had this notation for this. If I check, for example, this is a function where I do a bit string of a number 683, and let's do -1, right? And I see, right? So this is the integer number that corresponds, of course, to the bit string 0, 1, 0, 1, 0, 1, 0, 1. Right, so this is, at that point, I'm like, okay, this is a nice way of constructing this state, but it's also a bit silly, right? I mean, you just multiply matrices by flipping spins, and it would be much wiser to do this kind of analytically. And of course, this is what I promised in the beginning, where it can be handy to really understand, for example, these binary decompositions. Right, because I know that if I had like this decomposition of the integer numbers for my bit string as I had it written, right, it was sum I0, right, let me just actually take this, right, the full integer number was something like this. I write sum, so this is my number n of spins that I have. If I want to write an integer number with n bits in my problem, right, I'd have to do the bit di, this is the number which is 0 or 1, this is the bit, and then times 2 to the power I. Right, so this gives me an arbitrary number really as a bit string thing. And what I want to do is I want to kind of find out the inverse. I want to know what's the integer that corresponds to a certain bit string, which is the nail state. Right? But I know what I want to do is, so if I want to find the integer that corresponds to my nail state, right, what the integer will be, it will just be a sum, I equals 0, to now n over 2 minus 1. Let me write this down. And it's going to be 2 to the 2i. Right, because just every second bit here is 0 and the other one is 1. Right, so the first one is 0, then it's 1, 0 and 1, 0 and 1. Right, so I just write this as a sum of 2 to the power, sorry, yeah, no, it's correct. This is 2 to 2i, right? 2 to the power of the 2i. Right, and then I realized that this, for example, is really just like a finite geometric series here. So as a reminder, I know that if I have a geometric series with any number where I have r to the power 0 plus r to the power 1 plus and so on plus r to the power, let's say, m, right? And I know that this number s that I can compute here is going to be r to the power m plus 1 minus 1 divided by r minus 1. Right? So this is what how you solve a finite geometric series. Right? Which means, on the other hand, I can use this here because I realized that for this case, my r is really just 4. Right? I have exactly n half minus 1 terms in the sum. Right, so this number is just going to be 4 to the power n over 2. Sorry, I'm not good at writing at boards. That's why I use slides. Exactly, minus 1 divided by 3. Right? Good, let's see if it works, or if something was wrong here. Right, so instead of doing this kind of clumsy thing here, I can also just say, right, so here I had the number 683. So instead of using this, bit messy here. Okay, anyway, so let's write it. So what I want to do is I want to just get this integer number, let's call it m nil. Right, so this integer number would be, now in this case, right, so my n was, well, I just write it like n here, but I want to do n over 2, and I want to use again fully the integer arithmetic here, right, because I know that I'm going to get an integer, so I don't want Julia to use any of the floating point numbers here, so I just do n divided by 2. I do 4 to the power of n divided by 2. This will keep it an integer. Right, I do minus 1, and the whole thing I do divided by 3. And n was not defined, and in our case was 10. And what do I get? I don't get the correct number. This is of course 2. Why not? Did I use a different number in my thing? I get exactly half of that, so something. Okay, let me check. Let me just put this into the file here. Okay, 341. Maybe I did something wrong with the actual state before. Okay. I think I know what happened. Maybe I did. No, this is also fine. Okay, maybe my state is actually wrong. Let me just double check with the thing here. Sorry, I just want to get to the bottom of this. If not, we're going to keep going with this one. It's going to be fine. Okay, there was something wrong with this. Okay, no, this is the state here, and then this is. I think what I suspect is that something changed here with the ordering, because it could be 0, 1, 0, 1, 0, 1, 0, 1, or 1, 0, 1, 0, 1, 0, 1, 0. And I suspect something changed with the ordering here that I don't really know right now. But for now, okay, I'm just going to keep going with it. Homework, find out where the problem was. But so here I'm pretty convinced that if I look, for example, the bit string of this number that I have now, which was, what was it? It was 342. Right, and I always have to subtract 1, right? Because in Julia I start counting with 1, and usually I count with 0 in a bit string, and this is really also the, right? You see, this is the bit string here. I think before it was the other way around, and I think that was the difference. Okay, anyway, I don't want to waste much more time here. Just want to keep going. Okay, great. So this is what we had so far. Okay, so let's continue writing this function. So we have the initial state. Right, that's all I wanted to show. It's a very simple initial state. This nil state is also a product state. And I can construct it just by setting one element in this vector to 1. Right, and this one element should correspond to the bit string, which is 10, 10, 10. And if I think a bit about the math, right, I can spend a bit of brain time in order to not waste a lot of CPU time. In that case, could be good, unless you make mistakes as me. Okay, good. So then now this we don't need anymore, because before full diagonalization we had the full matrix exponential. This we cannot do anymore. The sigma set we still want to do. So this is exactly the same evaluation that I had before. So the line that I need to change now is this one here, right? So this was the evolution in the exact diagonalization, right? Instead of this, I want now to use this Krylov space method. So I'm just going to write down the function and then afterwards explain a bit more. Right, so I want to do this Krylov space exponential. The prefactor I want to choose is -1 dt. Right, so one could do two things. One could use just everything in this matrix A, or one can just define this prefactor here. This function will multiply this prefactor to the Hamiltonian before exponentiating it. And then I apply this to psi. And then I use these parameters that I used before. Krylov dimension maximum, let's use 20. And let's have it stop if the tolerance is going to be e to the -12. So this essentially means that, like, if you add this new line to this matrix A in your Krylov matrix, the norm of this matrix, if it's smaller than 10 to the -12, then it will stop the iteration. Okay, and that's it. That should work. Let's see if it does. Right, so now this function, if everything worked fine, it should give us again our matrix of SZ. And it's yeah, because I don't know how to write exponentiate. Nope. What? Okay, exponent. It's better to start from scratch. Exponentiate. You also need to know English really well if you want to code. Okay, and I get, again, the matrix. Everything should be much faster now. And, oh, I did not do any plot so far. Right, but I can, again, just, because here in this thing I got my SZ out, right, so I can do heat map of this out as SZ. And let's see what I get. I get something like this. Right, so now this is the same as I had before. Now I started with a different state. So I have this nail state, and I have this up, down, up, down, up, down, up, down, up, down. And it starts to evolve. And I want to discuss this now a little bit. Good, so let's go back to discussing the results that we have here. Right, so this is now the nice thing is now with this I can do much larger systems. Oh yeah, that's what I wanted to show still. Right, so now it's really easy. The simulation I did with 10, and remember yesterday I tried it with 12, and then it was already nearly crashing my laptop. Now if I do this with 12, I had no problem at all. Right, if I do it with 16, this is something where you see it gets a bit slower. But this is something where exact diagonalization would clearly fail. Now I can plot it again. Right, now I have it for 16. Let's see what I do here. If I do 20, why not? 20 is typically then something where it starts to get kind of slow. Let's give it a minute. Maybe it still works. Yes. But every step takes now quite a while, but it's still kind of doable and still kind of impressive. And if you have a big computer, you use this, you're smart about it, then you can really push it to almost 30 if you have enough time. Okay, good. So, but with this, let me now just stop with this here and just show some of the physics, just to motivate things again from a physical point of view. So, okay, now you can start playing with this. And here I was just playing with this a little bit. So this is for 22. This is, I think, where I didn't want to wait longer on my laptop. And I showed two cases here. This is the same plot as before. I start with this nail state, highly entangled state. So you put a lot of energy in your system initially. And then you just evolve this initial state with this transverse easing model. Here I have kind of a short-range interactions where this decay exponent in my coupling matrix goes down as 1 over r cubed. So this is pretty fast. This is almost nearest neighbor only, and then a little bit more. Here I really have alpha 1, which is kind of really long-range case. And you see something interesting, which is connecting to the lecture that we heard this morning. You see here that you start with this nail state, and then you evolve, and then everything becomes white here for this nearest neighbor case. Right? And why does it become white? Well, it's just because if I pick out one spin of the spin model in the center, for example, right, then think about it like all of the rest of the spins is going to act like a bath for that sim. Right? So you would imagine that at one point it's going to thermalize. Right? So it's going to go to a maximum temperature state in this case because the initial state is a very highly excited state. So you expect that it equilibrates to a very, very high temperature state, which is for a single qubit just a fully mixed density matrix. Right? So if you just wait long enough, you get actually a pretty boring result that all of the sigma z spin is going to be 1/2. Because if I take a mixed density matrix, I compute sigma z, it's going to be 0. And this is here in this color scale is white. Right? So it tells you also kind of a bit, if you want to do something, some quantum simulation experiment, and you want to extract something useful, you also have to look at some complicated observable that tells you something interesting. Right? Because here, after some time, sort of everything just becomes thermal, and every single spin observable gives you something boring in a way. On the other hand, if I go to this long-range case where I put alpha to 1, now there I see that these oscillations, they persist to much longer time, and they're kind of collective oscillations that you would expect. Right? So if this also becomes a quite trivial limit at one point, because if all of these spins talk equally to each other, then everything just becomes one collective spin that evolves as 1, and then everything is permutation symmetric. That again would be a very interesting, non-interesting limit, I would say. Okay, so this is just some of the physics that one can just explore. And so I just said, so one needs to look at some more complicated observable. So I'm going to skip this in the hands-on part, because otherwise it's going to take too long. But of course, one can also compute something like correlation functions. Right, so I'm just going to show you how one would do this in code, and I'm going to share the slides again. I'm going to make sure that they're going to be online. Right, I could, for example, just write a code where I have a sigma z connected correlation function, where I compute now for each point in time as a function of a distance between the spins. Right here I have sigma z for spin I. I take, for example, the spin number 3, and then I take another spin at position 3 plus d. So d1, 2, 3, 4, 5, I go further away from that spin, and I compute the correlation function between those, and I subtract kind of the trivial part, and this is what is done in this function here. So I'm going to show this, but this is one other thing to get to a more interesting observable. And then you can plot this, and you see already kind of now much more interesting physics. So you see, for example, that if I go to the short-range interaction case, if I look at this correlation, here this is a function of the distance between the spins, and as a function of the time that you have, you see that this correlation is kind of spreading out in this type of light cone behavior. Here it's a bit more clear because I show it on a logarithmic scale, so you see actually quite interesting physics. There's this light cone of information spreading, but you also get a little bit of sort of long-range connections between them. Or if I make the system now more long-range interactions, again, I get not more this light cone information spreading, but I get more this kind of immediate spreading of information between the system. And I just want to point out that like with this very simple code that we did here, very easy to write in 1.5 hours maybe, you can really kind of study now this type of physics of this correlation spreading, which is something that has been for a long time actually been kind of quite interesting in the literature. Also with these ion traps been done experimentally. And this is enough to spend a few hours here to kind of reproduce this type of physics if you want. Okay, great. So that's it for today. So that's the end. So as I had suspected, I will not make it to the open system part. I leave it there. It's kind of like written as a type of note thing. Maybe to give you one second message, this is master equations, review, and so on. You can use the exactly same code as I did here. You have to just redefine what your state vector means. Right? And as I said in the first lecture, state vector is something extremely general, just a bunch of numbers that tells you something about your system. So if I have an open system and I describe it with a big density matrix, right, all you can do is you can say, for example, you define your density matrix as a vector, so you just spread it out. So you snake through that, something like this, for example, going up, going down. So you write it as one vector of the elements. And then just with a little bit of thinking, one can do for a master equation, which is an equation governing an arbitrary open system, you can quite easily then also construct again your matrix A. And then you can reuse the exactly same code. And then I show you all of this. And then you get things like this, where you have now, for example, this nail state. You have this evolution of the spin. But on top of these oscillations, you now see that in this example also your excitations decay, as, for example, as a function of time. That's the one thing to do open system dynamics. A complete other methodology would be to use something which is called quantum trajectories, which means that you kind of pick on sample states from any mixed state that you have. But so any mixed state you can write as a statistical mixture of pure states, as you heard this morning. Like, for example, the maximally mixed state is just a classical ensemble of an excited state and a ground state. And you can just pick state from this, and then there's a stochastic prescription to evolve these states. And if you're interested to this, I have this in the rest of these notes written down. I'm going to skip through all of this here because I just don't have the time today. It's pretty cool. Then one gets something like this. One simulates a decay not just really as one expectation value of a density matrix, but one just simulates random stochastic trajectories. And if one uses more trajectories, one converges slowly to the exact dynamics of the expectation value. Okay, great. This is it. So this is the summary. Neglect the second part. I just didn't get to it. And I would rather skip this part because tomorrow I really want to get to the next thing, because really what we did so far is, in particular today, we did this Krylov space approach, which uses the sparsity of the matrices. But one thing we still not have really exploited yet is that we can make approximations to the state vector. Right, so everything so far was keeping a state vector fully exact. And still, this is a very big object, the state vector. It has a lot of information. And you can think about maybe you don't need all of this information in the state vector. And then if you want to push the system sizes larger, you may wonder then to really sort of compress the information in the state vector, use an approximate version of the state vector. And this is what I want to get to tomorrow. So tomorrow I want to start really with the mean field approximation, and then show you how to integrate mean field equations. Okay, sorry, I had a lot of stuff that I skipped, but that's it. So see you tomorrow.